So I'm going to do a little Torsor interlude. So to remind you what the situation is, so we arrive at the frame bundle, right? So we have a fiber bundle with a G structure. We can arrive at a frame bundle by looking at the trivializations in the structure, and it turns out that these trivializations will be a torsor. And what I want to explain is that torsors. So what I want to explain is that torsors slash principal homogeneous spaces are equal to principal bundles. So these are principal G bundles. See, these are kind of G torsors. So there's these two things. So this is the goal of what we're going to do. So what's the difference between these two things? So this is given in terms of actions. And this is given in terms of let's say fiber bundles with structures. Okay, so now I'm just gonna kind of continue rolling along. Let's give the official definition for torsors. So what is a torsor? So I'm gonna define two categories. They're going to be left torsors over X and right torsors over X. Need to go back to that. And right torsors right torsors. In each of these two categories, there's two flavors. There's kind of the geometric objects flavors, and then there's sheaves. And the geometric objects will always be sheaves. So so we'll start with this one here. Okay, so we're going to take so we'll do G over X. Okay, so here G is a well, I guess we should start with X. So X is going to be a site. G is going to be a sheaf of groups. Sheaf of groups on X. Okay, and then for this category here, the objects are going to be these things. They're going to be sheaves of sets on X. Plus, so I need to do a left action. So this is for the left thing. Oh, let me go back here. Plus an action. Here, G. Oh, what the heck? P cross. Crap! I did it again. G cross P to P, such that let's say for all T, GT cross PT to PT is full and faithful, so I want to define the category Tors G over X. Okay, and there's actually many ways to do this. So there's like, you can start in an arbitrary category. Or you can start with a category, in a category, in a site. A site. Torsors as sheaves. So we're going to take S to be a site, G to be a sheaf on S of groups, and then we're going to define here Tors G over X. Okay, so over S, and so this is going to be the category of left G torsors, and what we can do is so the objects is going to be a sheaf of sets, and these are going to have to satisfy some conditions. So one is that there exists a cover in S such that for all I, say I and I, this thing is not empty. Without this condition, it's called a pseudo-torsor sometimes. And then the second condition, it says that so let's say for all U and S, the action, let's say so it's going to be a left action, let's say plus action, row, so it's a left action. Okay, so what the action means is that for every open set U, we get an action like this. This is full and faithful. This full and faithful condition is the same thing as saying that the map, if I can make another map like this. Let's call this P of U cross P of U. I can call this gamma here. So this thing here is equal to rho with the projection onto P. And so what it does is it'll take a G and a P, and then it'll act, and then over here, and then it'll just project onto P. And so this is the graph of rho. Okay, and so what was I saying? I was saying that this full and faithful thing here, this condition, is the same thing as this is an isomorphism. This is a bijection. Okay, so what did I do? So all I've done is I've defined what these objects are, and so now I need to define what the morphisms are. And so the morphisms, these are just morphisms of G sets. So like i.e. equivariant maps. Fact is that all morphisms are automatically isomorphisms. All right, I'm gonna keep going. So the other thing I want to talk about is torsors as spaces. Okay, so for torsors as spaces, we're going to take X to be a space, and then so then I can define torsors G over X. So these are going to be left G torsors. Oh, so then we'll take G over X. So this is going to be a group object over X. So this is a group object in the over category over X. Okay, so then this. So now we're gonna define what this category is. So the objects here are these guys. So this is a P. So this is going to be the same category as the category of spaces here. So this is like schemes, maybe schemes over another base, with maps. And then such that, well, you can say 1 and 2. Pi has local sections. So, and here I'm abbreviating by saying local sections. I mean, again, that condition that there's a cover, and then for each guy in the cover, so it's a cover of X. For each guy in the cover, there's a section, and then in a section again is a map that goes from here to here, such that the composition is the identity. So it's just on an open set. It goes to P. Once you go down, it's just going to get back to the identity on the open set, and such that we could say for let's do it like this: G cross P to P cross X of P. So this is the graph map. So this is the action. Is an isomorphism in the category. Okay, and so like we said before, this is going to be the same thing as being full and faithful. Okay, and so then the morphisms in this setting. So these are going to just be G equivariant maps. As before. So note that so sheaves, or let's say so space type. Oh, where did I go? Space like torsors are sheaf-like torsors. Sheafy torsors. Okay, and so if you have one of these guys, then the sheaf This is the sheaf of sections of P. And then, and you're also, I guess, you're also given this guy here. Of sections of G. So this is how you go between the two. Okay, so this is kind of a standard thing. Okay, and so let me now define what a principal homogeneous space is. Or maybe I can actually construct a principal homogeneous space from a torsor. So suppose P is, let's say, a torsor, a left G torsor over X. Then what do we have? So there exists some cover of X, and so let's say that this map is like this. Okay, and then we have this G guy fixed. So from the axioms, there exists a cover such that P of UI contains some SI. Okay, and so given this SI, what can we do? Well, we're given a section here. We also know that G of UI cross P of UI here to P of UI is full and faithful. Faithful. Let's see. Okay, and so what this is going to happen, it's actually, this is actually for every U, okay? And so what this will allow us to do is this allows us to define, I guess this is for every U that's not empty. So what I'm going to do is I'm going to take P of UI, and I'm going to map it to G of UI, like so. And so this thing here is P restricted to UI. In the official definition is the fiber product definition. And this is the group scheme, okay, here. And what we'll do is we'll take an element P, and we'll map it to, we'll map it to well, I'm going to call it, I guess, P divided by Pi. And this guy here is the element, P divided by Pi is the element of G such that so let's call this G, such that G times P is equal to P, G times Pi is equal to P. Okay, so in particular you can note that that P over Pi times Pi, these two things cancel, and then you just get P back. Okay, so and since the action is full and faithful, this map here, let's call this phi Pi, gives an isomorphism. Actually, I'm going to claim a little bit more. The map phi Pi from this restricted thing, G of UI, is an isomorphism of left G of UI torsors. What does this mean? So this thing has an action. This has the stupid left action. Has the stupid left action. So this is kind of a claim. And let's do the proof here. Stupid left action, and this has a left action, and so what I'm claiming is that pi, and then we take g times p. Okay, so let's actually write this out. So this is equal to, so this is g p pi like this. So this is the element of g. And what is this guy? So this thing times pi, this is equal to gp. Okay, and p, so this is p, and this is really p divided by pi times pi here. Okay, so and then this thing here. Okay, so we can just cancel these two. So this is the left action here, and this is the left action here. These can cancel. So now if we go back down to here, so this thing is equal to g times p over pi, and this is equal to g, and then you have phi of pi p, like so. Okay, and so this tells you that this is a map of torsors here, of GUI torsors. This is the trivial GUI torsor, and so this is a trivialization. Okay, that's what we have. What am I moving towards? So now, what do I want to say? I want to say something else. So let me just do a lemma. I'm going towards the principal homogeneous spaces, these G torsors, left G torsors being the same thing as principal bundles. Okay, but let's look at automorphisms of G sets. So let P equal G. Okay, so this is review everything as just abstract groups, or abstract groups and sets. Okay, so I'm going to take P to be G, be the trivial left G set. Okay, so you take G, and we're going to view it as a set with a group action, where the group action is the stupid one. Okay, then the claim is that every G equivariant map F from P to P. So any automorphism of G sets. So this is as left G sets is given by right multiplication. By some element of G. 1 second. Okay, so where was I? I was talking about this. It is given by right multiplication by G. So the proof of this is let me get the pen back. So the proof of this is really easy. So what do we do? So we have P. This is G. It has the identity element. So this is the identity element. Okay, and the identity element is sent to some element. So we'll define the element that it's sent to by G. Okay, and now what we're going to do is we're going to look at how this thing acts on a particular element P. Okay, so we'll take a P arbitrary, F of P. Okay, well, F of P is just really F of P times E, because, okay, so this is just the way groups work. But now we know that this is a map of G sets, so P we can actually pull out. So P we can pull out, and so this is going to be P times, this this is going to be acting on f of e, and this is going to be g. Okay, and so what this tells us is that f of p is going to be, p times g. F of p is just going to be p times g here. Okay, and that proves that this automorphism here is just this. So if you take the trivial left action, or the trivial g set, g with left multiplication by itself, then the only automorphism that it's going to have is going to be right multiplication by g. Okay, and this is going to be really useful, okay? Because what have we done before? Well, we showed that, okay, so let me just kind of like go back here. So we had this claim here, and we showed that every p, which is a torsor, a left G torsor over X, has local isomorphisms. Okay. Let me rephrase this. So what did we show? We showed that every P, which is a left G torsor over X, is locally isomorphic to the trivial torsor. Okay, i.e. that we had this thing here. Then we had these covers, ui, or we had this cover here, so we had these open sets, and we can take pi inverse of ui, and then we knew that there were local sections here of P, and the local sections of P allowed us to define the trivializations, which we called phi of pi, for in this thing. Okay, so by the way, pi inverse of ui, this is just equal to pui. This thing was locally isomorphic to here, and this was an isomorphism of left GUI sets. Okay, and so what we'll be able to do is let me call this psi I. So what we'll be able to do is we'll be able to compose these trivializations. By the way, again, this is since G in this situation is representable, this is G cross UI. Okay, so we can compose them and look at the transition maps. Okay, so we compose them to form a transition. So here again we'll have so we'll take ui intersect uj. This is uij, and here we have kind of two trivializations, uij here, and we can do, say, trivialize with psi or trivialize with j, and so this is going to be uij cross g. This is going to be uij cross g here. And then, so we can go from one to the other, like we can go all the way around. Okay, so this would be psi I inverse composed with psi j. And we know that this psi, and let's call this psi ji, so this is from g of uij to g of uij, is an isomorphism of left G uij sets. Okay, so it's the left GUI actually torsors, right? And so we proved from the lemma this implies that that this psi ji is equal to right multiplication by some element of G of Uij. Okay. Okay, this is nice. So now, so to recap, what does this show? This shows every left G torsor over X is a G bundle with a particular G structure, a G structure where the transition maps are given by right multiplication. Okay, by some element of G. Okay, so this is nice, and this leads to the definition. And sometimes people can start this as the main object of study, but let's give this definition. So let's call it BGX. So this will be the category of let's say of principal G bundles, and let's say right transitioning principal G bundles okay, and so the objects of this category, and so these are going to be fiber bundles over X with a fiber G whose transition map are right multiplication. And then the morphisms, well, these are all actually torsors. All are torsors. So we take the multiplication to be sorry, so we take the, sorry, they're all torsors, so we take, so this is actually something that needs to be justified. So there is a natural left G action. Okay, and so this is kind of a lemma. So whenever you have this setup, where the transition maps are given by right multiplication, so the transition maps are all given by right multiplication. So this means that you can act on the left, and actually the transition maps are all going to be maps of torsors. They're going to be maps of G sets. So so left multiplication makes sense, and then this left multiplication actually glues together. Okay, and so the morphisms are just going to be morphisms of torsors. Okay, so there's some sneaky business that we need to get into. So sometimes you need to wear, that's pretty much everything that I wanted to say, but sometimes you need to worry about the difference between left multiplication and right multiplication. So what we can do is we can define these categories, so over X. So this is right acting. And then, so G is going to be right acting, and then you could have the same thing. You could have there also exists. So this is kind of some remarks. Also exists principal G bundles where the left action, so where the transition maps are given by left actions. Okay, that's all I'm going to say. I am going to post another video.